Hi everybody. My goal with this video is to address any of the missing content that would be in the remediation stuff that I've got on Classroom for you. So what I've got today is a lesson on nuclear chemistry, which sounds really scary perhaps, but isn't nearly as bad as you think it is. To start, we're going to go over the different types of events that can happen with the nucleus of an atom. So first up is fusion. Fusion is exactly what its name sounds like. You are fusing things together. So it's what happens when you take two elements and you combine them to make one new element. When you do fusion, you're going to get a couple of different things on the way out. But to start, you need some kind of energy at the beginning. So either things have to be moving really quickly or you need to have a lot of heat and pressure. But basically, you take two atoms, you crash them together with enough energy to hold them together, and they will stick together. In the process of doing that, all the extra energy that's there is going to be released, and you're normally going to release a neutron or multiple other pieces. Depends on what the pieces are that you put together. But that's the general idea, hence the picture on the right. When you're trying to solve one of these problems, meaning you're given this task and you have to fill in the blanks or you have to predict a product, you need to look at the mass number, it's the top left, and the atomic number, which is the bottom left. So for example, you've got these two hydrogen atoms over here. They both have a mass of 2, and they are both hydrogen, so their atomic number is 1, which means they have 1 proton. When you put those together, you're going to get 4 at the top and 2 for the bottom. So the new element is element number 2, because you added together 2 element number 1s. So it's 1 plus 1 equals 2. And then on the top here, the total needs to be 4. This one is actually more complicated than most of the simple examples would be. The most simple example would have just been 2 plus 2 equals 4. But 2 plus 2 does also equal 3 plus 1. They're both 4. And n over here is for neutron. So depending on what pieces you add together and how they are added together, you can get slightly different answers at the end. But basically, you just need to make sure that the pieces on both sides of that arrow equal. You can treat the arrow like an equals sign, because what it means is before the reaction on the left side, arrow means the reaction happens, and then on the right side of it is after the reaction. And all the pieces need to be equal on the left and the right side, meaning the mass and atomic numbers should equal on both sides. So on the left, the mass total is 4, and then on the right side of the arrow, 3 plus 1 gives you 4. It matches. On the left side for atomic number, you've got 1 and 1, and on the right, you've got 2 and 0, which both total to 2. Like I said, sometimes pieces break off because the product isn't stable. In general, if something isn't stable, it falls apart. So you can get the opposite of fusion as a result of the product that you make being unstable. And like I just said, anything unstable will break down by decaying. That can happen in a couple of different ways. First one is fission. Fission is like the opposite of fusion. You're taking one thing and you're breaking it into 2, meaning you have one element and that one element breaks into 2 or more. It's usually 2. In this case, you take a neutron on the left there and you crash it into uranium. And if you've ever heard about what uranium is used for, it is for making bombs, among other things. And it is very heavy and it's very easy to make it unstable. So if you crash a neutron into it, it adds that mass. So that's why it goes from 235 to 236, because 235 plus 1 is 236. Atomic number stays the same because the neutron here has no atomic number. And what you made here is unstable. Since it's unstable, it has to break in order to do so. If you were carrying a pile of books and you made it unstable, the pile would break apart into the individual books, or at least a couple of piles of books, right? So anything unstable will break apart or separate in order to become more stable. When you do this, you're going to release a bunch of energy, just like with fusion. And the total of all the pieces should add together. So for example, the top number is 236. So we should be able to add together these pieces and get 236. And if you notice, 92 and 141 is going to give you 233. And there are 3 neutrons, so 233 between these two, 234, 235, 236. And then the bottom number should add up to 92, because that's what we started with. 36 plus 56 is 92. So just like with fusion, all the pieces need to add up to each other at the end. All right, so next I'm going to show you this little clip here. I'm going to ask you to try and figure out how you think this is related to fission. So, how do you think this relates back to fission? And I'll give you a hint. This is the start of your fission. So if where the ball hits there, notice that there's a lot more ping pong balls in there. And there's one moving by itself. One ping pong ball gets into here, it lands, it crashes. When it does so, it shoots all the other ones all over the place. Basically, this is a representation of a chain reaction. And fission can happen as a chain reaction. Notice how at the end of this there were 3 neutrons? Each of those neutrons can then shoot off and start this process all over again. So that means that one fission reaction can then create 3 fission reactions. Each one of those reactions will get you 3 more neutrons. Each of those neutrons can make another reaction. So you're magnifying it. And as you do that, it's going to keep going. The follow-up question to that is, when would this process stop? And the answer is pretty simple. Just like with this video here, the process stops as soon as you run out of stuff that you can break apart. And that's going to happen once you get to things that are stable. You run out of neutrons flying around, or you run out of energy. Notice how once the ping pong balls are all sitting there on the ground, process is done. All right, so next, we're moving on to radioactivity. These happen on their own. You don't need anything else to make these things happen. When you have an unstable element, an unstable isotope of an element, it means that they're going to break down on their own. Notice in the other ones, you had something crashing into the element to start the process, or you had energy added to start the process. You don't need that with radioactivity because it breaks down on its own. These are always going to be with elements, well, for the most part, that have extra pieces of something, either extra protons or extra neutrons or extra energy or something like that. But basically, or extra relative to everything else, extra electrons, which would mean it's too few protons, not too many electrons, really. But when that happens, it'll break apart. The three types that we are going to care about are alpha, beta, and gamma. So these are all types of decay, meaning a thing breaks down on its own. You have alpha emission, beta emission, and gamma emission. Notice that out of the three, two of them break off an actual part of an atom, and one of them is releasing energy. And the one that's releasing energy by itself is gamma. It's releasing radiation, but it's electromagnetic, meaning it's a wave like light or something like that. Or gamma rays, because it's gamma radiation. All of these have different strengths. So alpha, you can block with a piece of paper, but beta and gamma would go right through the paper. Beta would get stopped by a piece of aluminum foil, but gamma would go right through it. And in order to try and stop gamma, you would need lead. Here's the problem. Notice how you've got some gamma going through the lead? Depending on how thick the material is, it might not actually stop the gamma radiation. So gamma radiation is strong. It goes through like everything. It's part of why it's so dangerous. It's one of the reasons why certain radioactive elements are so dangerous, because, well, it's going to pass through things on the way. And if it passes through your cells, it can mess up the cells really badly if it just goes through. Imagine it's like a tiny chemical bullet, and it's just flying straight through, and it goes in one side and out the other. So anyways, that's why radiation is so dangerous. So first type is alpha decay. Alpha means you lose a helium nucleus. Helium has a mass of 4, and it has 2 protons, so that example right there of uranium breaking down is alpha. Every alpha reaction, every single one, every alpha decay reaction is always going to make that helium at the end there. And that's because that is what's called an alpha particle. The helium there is an alpha particle. So notice how the top number here starts at 235, goes down to 231. That's a difference of 4, which means you have 4 for the mass on the top. Atomic number goes from 92 to 90. That's a drop of 2, and that accounts for the 2 protons over here for the helium. Notice how all the parts add up on the top. 235 equals 231 plus 4. And on the bottom, everything adds up. 92 equals 90 plus 2. Same thing is going to be true for beta decay, except for beta decay, you are releasing electrons. It's right over here. Technically, this is beta emission. You could do the opposite and add it at the beginning, but we're not talking about that. We're talking about the normal type of beta decay. And since electrons have no mass, at least as far as we're concerned, there's no change in mass. What might seem a little weird is that the atomic number changes. But if you look at it, electrons are treated as -1. And since the electron is treated as -1, the numbers still add up. 92 equals 93 plus -1, which is the same as 92 equals 93 minus 1. Next, we've got gamma radiation, and gamma radiation releases energy and relaxes or releases the energy that's left over, that's being stored in the element. It has no mass and it has no atomic number, so there's a little issue on the page there, but the mass doesn't actually change. So I left out some blanks here, and in order to solve these, you would do the reverse of what's missing, meaning if you have 235 on the top here, and there is something added to something that's in the blank here, to fix it, you're trying to solve for whatever is missing, you need to move this over here. So to do that in algebra, you have to do the opposite. So you've got 235 minus this 4 over here, so the top number would be 231. For the bottom, you've got 92 equals something plus 2. Well, what number plus 2 would give you 92? To find that, 92 minus this 2 would give you 90. If you repeat this process for beta, you'll notice that you also get the same answers there. So numbers should all add up. Like I said earlier, the gamma decay example is a little off. you'll very commonly see that the gamma decay ones don't have any change in the mass at the top there. All right, next on the list is half-life. Half-life is the time it takes for half of one of those radioactive elements to decay, meaning the sample of it as a whole. So that means after one half-life, you're going to have half of the sample that you started with. After two half-lives, that is half and then half again, which means a quarter is what you'll have left. So if you start with 100 grams, start with 100, you go through one half-life, meaning the life for half of your sample. That 100 grams is now broken in half to 50. Okay. If you start with 50 now, after another half-life, you have half of it. Goes to 25. If you go through another half-life, that's going to cut in half again, 25 down to 12 and a half. And you repeat this process infinite times for every time you add a half-life. Easy way to visualize this, you start with 100 radioactive atoms. After one half-life, half of them have decayed now. So you've only got 50 out of 100 left. Notice that the red ones are radioactive, the gray ones are not. So you go through another half-life, half of the ones that were in here decay. So now you only have a quarter as many as you started with. So you went from 100 to 50 after the first half-life to 25 for the third one. If you repeat this again, you're going to get 13, because if you look back at the math over here, that is what 12 and a half rounds to, 13. Notice if you keep going through this process and you keep cutting it in half, theoretically, you should never get to 0, because if you keep cutting something in half, you always have half of that left over. In reality, eventually you can run out of radioactive atoms, but it should take a while, because assuming you start with a realistic number of atoms, which is going to be way more than 100, it's going to take a very long time for you to keep splitting it in half down enough to get down to 0. And then the last topic we need to talk about is radiation from light. And light radiation is something that normally happens when an atom absorbs a bunch of energy of some type, and then it releases that back as light. If you've ever seen those glow-in-the-dark stars, or you've seen like glow-in-the-dark paint or something like that, they absorb light during the day, and then they release it. You can't see it during the day because it's much less bright than the lights that you would see in the room. But once it's dark, you'll notice that it's giving away light. This is because it's absorbing and then releasing the excess energy that it got. This is also what happens during a flame test. So if you think back to earlier in the year where you lit all those different salts on fire and they were different colors, that was this. When you burn those different chemicals, they're making all those different colors because they're releasing different amounts of energy. And those different amounts of energy, as you can see in the table over here, correlate with their wavelength, and their wavelength correlates with the color. So different colors have different amounts of energy. To prove this, and to see that every element releases its own unique set of colors, meaning it is different in the amount of energy, you can use something called a spectroscope or a diffracting gradient. A diffracting gradient is this little square thing. You're going to see what happens though. So every element has its own unique pattern because every element has a different number of protons. It'll have a different number of electrons. And as that happens, that means the nucleus is different, and it means the path for the electrons moving is different. So it takes a different amount of energy to move all of them around, and because of that, you get different colors. So each different sample here is going to be different colors. You can do this with any element, and you'll always get a different pattern. Some elements have similar patterns, but there are no elements that have the exact same pattern. And because of this, you can actually identify what's in a sample of stuff by doing this. So like NASA uses this to figure out what planets like atmospheres are made of, because they can do this with the gas from their planet's atmosphere and stuff like that. It also helps a lot to figure out like what stars are made of and things like that, because they know the patterns for the light. We don't really care about molecules for this, we just care about atoms. but it's the same basic idea. Crime scene investigation units have used stuff like this before to identify what a substance is. They can use this in water treatment plants to figure out if there's impurities in the water and stuff like that. There's actually a bunch of different uses for this, and it only works because of the radiation or light that's being released from the elements as they burn. So the final part to this is using spectral lines to identify stuff, like I just said. A couple of questions that you may have seen that look like this. Basically, if you know what the patterns are for the elements that you've got, and you look at a mixture of those things, you can figure out what it's made of by looking at what lines are there. So if you look at the picture at the bottom here, that's the mixture. If we're looking for which elements are there, you want to find the ones that match it. And pretty quickly with this one, you can see that these lines match, these lines match, these lines match, these three match these three, these ones match these ones. So that means strontium is definitely there. If you look at the one above it, cadmium, none of the lines indicate that it's there. There's one line that looks like it should be there, this one, so it might make you think that it's there, but then if you look back up there at lithium, at the very top, notice every single line on lithium matches. In order for it to be there, all of its lines have to match properly. So lithium matches perfectly. All four of its lines match. All of the strontium lines match. And cadmium, the great majority don't even look close. So because of that, this mixture is made of strontium and lithium. It is not made of cadmium. And at this point, hopefully I've answered any questions that would have come up when going through there. But if not, please make sure you leave some comments in Google Classroom if you have any questions.